Okay, so my name is Daniel Nikpayuk. My talk is lessons learned while coding my first functional type system in constexpr C++. Before I start, I just want to say I'm actually going to go through a lot of content, so I'm going to read very quickly. Think of it more like a survey. I don't expect you to follow absolutely everything, but if you have questions at the end, or come see me after, or it can be reviewed later. Okay, so outline for my talk. There are 6 parts. So about myself, about this talk, template metaprogramming, context for programming, my functional type system, and lessons learned. So about myself, who am I? I'm a self-taught coder. I've been programming in C++ since 2005. I don't currently work in the tech industry. I have a Bachelor of Arts majoring in mathematics, minoring in economics. I'm an Inuit person, specifically Inuvialuit from Canada's Western Arctic, and devoted to the continued renewal of my field's language and culture. So why C++? It is a life goal of mine to build a programming language for multimedia production. I hope to offer said language as an option for telling and retelling my people's stories, traditional and new. Such a language will generally require systems level performance, and so C++ is a good fit for writing its first compiler. Okay, about this talk. What is this talk about? As per the title, it is primarily about functional type systems and constexpr C++. So let's start with functional type systems. A brain on terms is often a good idea, so I will say for the purpose of this talk that a functional type system is one which is built on top of the untyped lambda calculus. The types of these systems include atomics, such as booleans, characters, and integers. They also include compound types, such as products, coproducts, and lists. Beyond this, it is worth noting that in practice, the untyped lambda calculus can in fact be equipped with alternate theoretical type systems. These theoretical type systems are related to each other, and those relations are encoded into what's called the lambda cube. So in practice, such type systems are built on top of Lisp-style programming languages, which resonate well with the lambda calculus. A type system, when implemented, can be thought of as a record-keeping system. In particular, though, it is not only meant to hold types, it is expected to hold values of those types as well. The difference between theory and practice here is that real-world type systems come with real-world constraints. In terms of my type system, it extends the core types by further including comparison types, such as the identity type, as well as logical types, such as dependent products and dependent pairs. I should mention, my functional type system has a few additional constraints as well, some which might be unique to it. In particular, it is required to be serializable. This means, as a record-keeping system, it can be transmitted across mediums of technology. In effect, it means it can be saved and reloaded for later use. Furthermore, the internal representation of function values is required to be a bytecode in the style of assembly code. The bytecode representation itself has an additional requirement. Its instructions can only request memory from the stack, cannot allocate from the heap. If these constraints seem arbitrary, they're not. We'll go into greater detail as to why in the following sections. So this brings us to constexpr C++. Rather than starting from there, though, it is more beneficial for us to instead discuss compile time programming more broadly, in which constexpr C++ is only one part that makes up a greater whole. To continue then, if we were to observe the evolution of programming languages, it could be said that once types were introduced to a given language, they then gave us the option to translate programs of that language into 2 parts. First are those parts that are runtime invariant, and so are known completely at compile time. Second are those parts that can only be known during runtime execution. Given this, once types are introduced into a programming language, they allow us to distinguish between time scopes, in particular between compile time and runtime. Relative to this talk, any program evaluation which manipulates runtime invariant data as input and returns runtime invariant data as output is known as compile time programming. So this includes static types, which are known completely at compile time. With that said, modern languages such as C++ take this further by allowing for the manipulation of runtime invariant value data as well. Okay, so two examples are as follows. The first is an int x, we assign it the value 5. We annotate it constexpr, and then within a struct, we have a unsigned array, length 3, and we mark it constexpr and static. So that's it in terms of constexpr C++ for now. So to end this section, I would like to add that this talk is also about design, especially broader ideas of design, which for my part includes cultural design. And so before we get into more technical details, I would like to take a short detour regarding cultural design. I would like to center Inuit design using a phrase in Inuktitut, Inuktitut being the umbrella term for my people's language. As for the phrase, sila isuma talmat. To translate, sila is weather, isuma is thought, isuma ta is boss. So sila isuma talmat is weather is boss. Okay. In classical Inuit cosmology, there's a deep connection between sila and isuma. So I took this picture in Nunavut in 2002. I took it with a disposable camera, so it's not the highest quality. But what happened was it was completely clear sky. And then within literally like 10 minutes, these clouds rolled in and covered it completely. And the clouds are moving so fast, it just like shaped the front of the clouds and like smoothened it out. So weather in the Arctic changes all the time, and it changes quickly. This parallels human thought. To take this interpretation further, ideas of weather are connected to air, and air is connected to breath. When humans breathe, we take air into our lungs, circulates through our bodies, and then leaves us. What happens when we use such breath to speak? The air has passed through our brains, and so our thoughts have effect on it, meaning when it leaves us as we speak, it conveys our will out into the world. It affects the world. It is for this reason, Inuit traditionally have been very careful with our words, since we know the power that they hold. Okay, so what does this story have to do with cultural design? Inuit culture is shaped by thousands of years of Arctic living. The ice and the snow are both water and are malleable. In this sense, there's very little permanence in the Arctic. And so in an environment like that, the things that have great meaning are the things that are permanent. So what is permanent in Inuit culture? Isuma, which is to say thought, or rather patterns of thought that persist. Anthropologists and ethnographers who have studied Inuit society have noted a great many technologies that my ancestors have innovated, such as Igluit, Kayait, and Kamutit. But material technology in the Arctic is malleable. As for the technology that is permanent in Inuit culture, Isma, our ways of thinking are our technologies. In any case, all this is my way of saying this talk is very much about design, especially ways of thinking about design that persist. Okay, so next section, template metaprogramming. So before we get into constexpr, C++, and functional type systems, I would like to first discuss template metaprogramming. Historically speaking, template metaprogramming is a paradigm shift from standard C++. It is a different way of thinking about C++ code. To motivate this understanding, I would ask, how do we use programming languages? In a general sense, that is. Programming languages, generally speaking, describe types and values for those types. Such types can range from simple built-in to complex data structures with corresponding objects as values. From there, we usually go on to define functions which act on our types and values of interest to return other types and values of interest. In a general sense, this is pretty much the core of what programming languages are and do. I say this because most other grammatical features added to a language are there to keep types, values, and functions organized. Either that, or they are there to validate and verify type logic under additional constraints. So given this, I would further say that the real focus of a programming language is that of functions. How does this apply to template metaprogramming? Template metaprogramming at its simplest is a way to grammatically hack the C++ compiler. Compilers, for everything they are also programs. In their behavior, when compiling, they branch and loop based on their input, just like any other non-trivial program does. It is worth pointing out that the input to a compiler is, in its simplest terms, really just strings of characters which then go on to form our programs. Template metaprogramming is a style of such which uses language features in unintended ways to redirect the compiler's behavior. When done right, it ends up executing side programs on top of the main program translation. A classic example of that, a classic example is that of a conditional operator. So here we have a constexpr bool value called dispatch. We declare a type alias, and then we define it using conditional, and the dispatch, or based on the dispatch, it will return double or int. And then we can finally define a value based on that type. Okay, so the higher order idea is that we conceptualize certain C++ grammars to take types and values as compile time input. Pretending like those grammars were regular functions in the language. In effect, we end up with a higher order programming language built on top of standard C++, one which evaluates at compile time rather than runtime. Conceptualizing grammar this way has been quite useful to C++ programmers in the past, which is why it has become a full-fledged style of programming on its own. At the end of the day, though, it is important to remember this is just another programming tool, which, like any other, has its trade-offs. On the upside, it allows programmers to resolve relevant data at compile time, which is good for program performance. It can also be used to dispatch type traits and attributes at compile time. On the downside, because it is a hack, because the compiler doesn't recognize or conceptualize in certain grammars to be meta functions, it ends up shifting some of its type checking to the programmers who are making use of this metaprogramming style. As of C++ 17, variadic templates, alias templates, and class templates can all be conceptualized as meta functions. As with standard C++ functions, each has its own grammar for making a function call. So standard C++ functions use parentheses in their definitions of functions, as well as the function call. Variadic templates, as meta functions, are the variety which most resemble standard functions. As such, we will discuss them first. So variadic meta functions take a mix of parameters as input and return a value as output. If you'd like to use a value as input, I recommend using the auto keyword. So here we define a square function using auto. And then when we call it, instead of parentheses, it has the left and right braces. And we call it the value 2.0. So in effect, such meta functions are weakly typed because although the auto keyword does restrict input to values, it doesn't restrict any further than that. Meta functions such as these can be strengthened in C++ 20 using concepts. So here we have the integral concept. We re-implement our square function Same as before, except this time we test its type to see if it's an integral. And then when we call it on the floating point number, it returns an error because that's not an integral. Okay, so continuing on, an interesting artifact about variadic metafunctions is that we can define them using common pattern matching paradigms already known in other languages. A classic example is from Haskell. So we declare our factorial. It also has an integral concept, except I think they call them type classes. And then we define our factorial by case. The base case maps 0 to 1, and the general case maps the variable n to the recursive definition. In C++, we do the same thing using specialization. So we have a factorial. It takes auto n input, but this is the general case. And then we specialize to define the base case that maps 0 to 1. So moving on, let's next observe alias templates. Alias templates are similar in their input to variable templates, but because they are aliases, their output is restricted to types. So we have a makeIntArray metafunction. We declare it with using. It takes auto n as input and returns a std array of type int and size n as output. So that's it for alias metafunctions, except it's worth noting that pattern matching isn't an unavailable feature. Finally, we come to class templates. As metafunctions, they are similar to alias metafunctions, but with some important differences. Class metafunctions always construct classes. This is in contrast to aliases, which are able to return pre-existing types. Class metafunctions also allow specialization. This means that pattern matching is an unavailable feature. So for example, we have some metafunction, we mark it with class, it takes a type as input, but then we can specialize an alternate case where the input is known to be a constant type. Okay, so that's it for the 3 kinds of metafunctions. Let's now discuss some of the traits they might share with functions at large. The first kind of function worth mentioning is that of a higher order function. In that case, what does it mean when we speak of higher order metafunctions? In programming literature, higher order functions are ones which take other functions as input or return other functions as output. In template metaprogramming, all 3 metafunction varieties can take other metafunctions as input. Unfortunately, variable metafunctions are not supported as input to any of the higher order metafunctions. As for alias and class metafunctions, they can be passed as template parameters using template keywords. So here we have a higher order metafunction. It takes a regular metafunction using template syntax, and it also takes a type as its input. In its body, it applies that metafunction to the type and then does other things. So as for returning metafunctions from other metafunctions, there's currently no direct support for such a feature. Before moving on to other kinds of metafunctions, one higher order metafunction worth mentioning is that of apply. So here is apply. It's kind of the same as before. And if we had defined this first, we could have refactored the previous example. So the next trait metafunctions can have is that of recursion. In fact, we've already seen an example which implemented the factorial function. There's not too much else to say except for a subtlety having to do with how compilers evaluate metaprograms. Let's start with an example to demonstrate. So we have the factorial function again, but this time we define it using the ternary operator. Does this compile? No, it does not. Both GCC and Clang give errors saying the template instantiation depth has been exceeded. So why does this happen? Because of the ternary operator. To explain this, let's observe the following expression. So the function f applies the values g of x and h of y. So I ask, how do we evaluate such an expression? We can first evaluate g and h, the order of which doesn't matter here. Then we can pass the return values to f. The style of evaluation is called eager evaluation. Alternatively, we can treat g and h as paused expressions and pass them to f. The meaning here is that we only evaluate g and h if the return values are actually needed when computing f. This is called lazy evaluation. So the problem with the ternary operator is it evaluates eagerly. This means the expressions n equals 0, factorial of n minus 1, and 1 are each evaluated before they're passed to the ternary. For any int input n greater than or equal to 0, this becomes a problem when we reach the assigned value n equals 0. By trying to evaluate factorial of n minus 1, we're trying to evaluate factorial of minus 1, which keeps decrementing by its definition and thus never halts. So the compiler is itself forced to halt when it exceeds its preset template instantiation depth. To finish our discussion on recursion, I'd like to show yet another way it can be achieved. We've already observed variable metafunction recursion, so here I will demonstrate class metafunction recursion as an alternative. It's worth stating, though, that class metafunction recursion is less performant at compile time. It's worth knowing about because of its historical relevance. It's also worth knowing about because recursive class metafunctions further introduce a class template as compile time tuple pattern. It probably has a better name, but if it does, I don't know what it is. The idea is that C++ classes naturally have member values, types, and functions. So if we declare member values or functions to be static, they become shared between objects of the class. In effect, this means static values and functions belong to the class type rather than any given object of that class. This is notable for us because it means we can access static members of a class using the scope resolution operator. So here we have a meta pair definition. It takes the two type input, assigns them as first and second member types. And then we can specify an actual meta pair and then access its first member. I should mention, in this talk, I use the class and struct keywords interchangeably. For our purposes, the only difference is classes default to private members, while structs default to public. As for recursion, we can use classes as beta containers to re-implement the factorial function. So now we have a factorial tuple. It has a member value, called value, which defines the general case. And then we specialize the base case, assigning value 1 to the member value. And then we define the factorial meta function itself using the factorial tuple accessing its member value. Okay, so to finish this section, I would say the final function trait worth mentioning is that of currying. Currying is where we apply a multi-argument function to a single value to get a partially applied function back. With standard functions, it can be implemented in C++20 as follows. I'm not going to explain this one, I'll just leave it up for a second. So unfortunately, because this requires returning a function from a function, it is not directly supported in template metaprogramming. There are multitudes of workarounds, but they are beyond the scope of this talk. Just gonna have some water quickly. Okay, so constexpr programming. Template metaprogramming hacks the compiler, in effect getting it to act like an interpreter as a side job to its main purpose. Another way to say this is that the compiler is taking on extra responsibility that it wasn't designed to handle. Arguably, there's nothing technically wrong with this so long as we adhere to the C++ specification, but from a design perspective, it is questionable because it wasn't engineered to be an accountable unified system. What's more, even if we could logically prove it adheres to a clean, scalable design, the grammatical complexity of template metaprogramming remains a heavy burden. So constexpr programming aims to fix these problems because it intentionally designs for them. In constexpr programming, we can write standard C++ code, but instead of being translated into assembly, the compiler runs it at compile time. So long as we annotate it with the constexpr keyword, which we've observed many times at this point. There is a caveat. The constexpr keyword doesn't promise to run the code at compile time. Generally speaking, it does so if it knows it can. Otherwise, it considers the code as standard to be compiled the usual way. Strictly speaking, it's not as simple as that, though. C++ support for constexpr does not apply to the whole of the language and varies based on the exact specification being used. To keep things simple, we'll put aside such caveats for now and say there are primarily two ways to run constexpr programs, with functions and with classes. So constexpr functions are defined in the same way as standard functions, a C++20 example being just a +2 function, which takes a value and adds 2 to it. Furthermore, we call constexpr functions the same way as standard ones. Unfortunately, there are some restrictions in their use. One of the most notable is when we pass compile time values as arguments. To anthropomorphize, from the perspective of the function, it has no way of knowing if the value it's been given is compile time or not. So it treats the value as if it's runtime. This restricts the way we can interact with arguments inside a function body. So for example, arguments cannot be passed as template parameters. So here we have a square plus 1 function. It takes an auto value x and then tries to pass it as a template parameter to our previous square function. So when we define an actual constexpr auto value x and apply the square plus 1 function to it, we get an error. And yet, there is a relevant but narrow C++17 workaround, which I call the type name autocorrespondence. The idea is we can convert a type to a value and convert it back again. As for how it's implemented, we start by defining a void function template. I've named it store. It takes a single generic value as input and does nothing with it. We then define our meta function. So uStoreT, so the base case takes a type and embeds the type with an added pointer into store. So the single reference case just preserves the single reference and embeds it into store. And then the double reference also preserves the double reference into store. So the reference type cases encode themselves into store, but the default case where we add a pointer does not. The only reason for this special case is due to the void type. C++ does not allow functions with void input. So this would not compile. On the other hand, C++ does allow functions with void pointer input. The trick then is to add a pointer to every non-reference type in the conversion. As for converting back, we simply pattern match the cases and remove the extra pointer. Okay, so in the double reference case, it just preserves it directly. In a single reference case, same thing. And then the type with pointer, we just remove the pointer and return back the type. So to which we can then restore our original type. So we have, instead of u store t, we now have t store u. It takes an auto input called u, gets the type from it using decal type, and then calls t restore t, where t restore t takes a type as input, normalizes it as a const reference. That's actually just an optimization to simplify various cases, and then applies or pattern matches using store match to get the result back. So note in the previous slide the use of t restore t, which takes the type of the store function and returns the original type of interest. So this is our workaround for the constexpr argument problem. We pass a compile time function pointer as argument, which we then convert back to a guaranteed constexpr value. We do so by first restoring its type and then converting back to a value. It is an artifact of function pointers that we can do this. As for an example application, so here we have a function called our different. It takes two types as input. It uses those types, restores them, and then applies the restoration, or applies the same to those restorations, and then negates. So if you were to use it in practice, you could convert an int to a value, you can convert a character to a value, and then apply as arguments, apply those as arguments to our different, and it compiles under a static assert. So that's the trick. It should be said in C++26, all this can be achieved directly with reflection. As for the history of this type name autocorrespondence, it wasn't the constexpr argument problem that originally motivated this technique. It was the need for uniform metafunction parameters. So here we have our apply function, or higher order metafunction. Takes regular metafunction and type as input, and then applies. But we have a second version. It again takes a metafunction, but instead it takes a value this time and applies that. So the point of these versions of apply is to show that distinct parameter kinds lead to otherwise duplicate metafunctions and often duplicate algorithms. The way to mitigate this is to convert all auto parameters to type name parameters, or to convert all type name parameters to auto ones. I will mention in my own code library, I've chosen a type name to auto conversion policy because it allows us to pass values as template parameters, as well as function arguments. It also tends to have better compile time performance, but that is case by case. Okay, moving on. Another restriction of constexpr functions worth mentioning is called the constexpr allocation problem. Basically, the problem is that objects with heap allocated memory cannot currently be returned from constexpr functions. In practice, this policy is strict enough that class objects with internal pointers also cannot be returned from constexpr functions, assuming they're saved as constexpr values. So note that allocating heap memory within the compile time scope of a function body is often supported. Also, it's worth saying that to varying degrees, there are proposals to solve this problem. At the very least, more recent versions of C++ offer greater support for standard library containers beyond that of std array and std vector. In any case, that's it for constexpr functions right now. So on to constexpr classes. Defining them is a bit more involved than for functions. Independent of their variations, we at least always start by annotating the constructors of a class. So here we have a class called opacity. Here's a constructor for it, and we mark it as constexpr. And then independently of that, we can mark member functions as constexpr as well. So note that when we instantiate a constexpr object of the given class type, it is first created under the rules of its constructor as if it were a runtime object. Once the object finishes its construction, it is assumed to be an immutable compile time object. It's worth mentioning the same pattern occurs with the constexpr functions as well. When a constexpr function is called, it is executed as if during runtime, but when the value is returned and assigned as a constexpr variable, it effectively crystallizes as an immutable compile time object. The prevalence of this pattern merits some terminology to help us conceptualize and navigate its subtleties. Notably that of time scopes, in particular metacompile time and meta runtime. So here we have a program lifespan. It can be split into compile time and runtime, and then the compile time can be decomposed into scopes of metacompile time and meta runtime. So I've introduced this terminology in previous talks. I stand by it. It has helped me sort out designs that would otherwise have been too confusing to implement. And I know of no standard terminology which does the same. Ultimately, this pattern and terminology leads to an idea I'm calling the compile time monad. It just means in practice, compile time programming works by alternating between scopes of meta runtime and meta compile time. So that's it for constexpr classes. So continuing on, excuse me, sorry, one moment. Okay, since constexpr code is largely just regular C++ with the added constexpr keyword, there's not too much else to say about it. As such, the remainder of this section will focus on building a theory of functions within this context. To start, given the nature of constexpr compiling and being able to run programs at compile time, it is natural to search for ways to automate the construction and manipulation of functions. In particular, we focus on the idea of composition. So for this exposition, I will use simplified function notation or pseudocode. So manual composition is simple. This is just your standard math definition of compose. To translate this into automated composition, we first switch to an alternative form known as continuation passing. So we take a regular function f and lift it to become continuation passing. As a CPS function, we then evaluate it. Notice the right-hand side is nearly identical to regular compose, just the function's inverted. One of the reasons continuation passing functions are interesting is because they have their own composition operator. If f and g are CPS functions, then their composition is defined as follows. Just leave that up for a second. Okay, so for those interested, I have a compiler explorer link implementing CPS compose. Okay, so now, for the purpose of my functional type system, we will want to generalize CPS composition in a way that lets us abstract out a controller. Think of it like this. If we want to compose a chain of functions, f0, f1 through fn, we can, instead of specifying a sequence of actual functions, index them numerically. Then we would only need to specify the corresponding numbers. So now a sequence of indices k0, k1 through kn to create our controller. So using C++ pseudocode to keep the details relatively simple, we could implement our abstract CPS functions as follows. So we have our function. As a template parameter, it takes a controller value. uses that controller and a getNext function to create our continuation. And then it returns a call of that continuation to an intermediate value. This is a template pattern. Sorry, I shouldn't use the word template. It's a general pattern. Yeah. Okay. The idea is we can, in practice, implement a controller as a compile time byte array. We can then use that byte array to get the next CPS function in the composition. We then call that next function, making sure to pass the byte array along its compile time trajectory. So it can continue the process until a function is constructed. With this, we now have a powerful technique for automating the composition of functions. And yet, we can take this technique further. I won't go into the details here, but we can generalize our abstract CPS functions to act as if they were register machines. In turn, the controllers for these more powerful CPS register machines would be encoded as tables instead of arrays. This would then give the appearance of a bytecode assembly language. This is the topic of my 2024 talk, C++ as Metacompiler. Given this, I'll skip the finer details here. I will add the main grammatical feature we need to make this idea work is that of variadic packs. A C++20 example would be nothing fancy here, it's just some function with an auto pack of arguments. The reason for needing variadics is that we are simulating an arbitrary number of registers as CPS function arguments. In particular, we will need to read from and write to any given register in the pack. In other words, we need variadic indexing. C++26, this is simple since there is direct language support. An example being, so here we have a auto pack and we want the fifth value. And so with 26, you have an array-like indexing, but for a pack. Very simple. In my own library, I'm using C++17, so it requires a number of carefully crafted tricks outside the scope of this talk. Finally, to finish this section, I thought I'd give an example of what CPS register assembly actually looks like. There's no zoom, and I'm not going to explain it. I'll leave it up for a second. I apologize. Audio's okay? Bit of static. Okay. Okay, next section, my functional type system. We're finally ready to discuss the type system that makes up this talk. I previously mentioned that I'd restricted my functional type system in ways that might be uncommon. That's it.
Oh, yeah. That's good. Sorry, guys. That's broken. The rest of these top secret.
Okay. 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 So Right. So my functional type system, notably, my type system requires serialization, meta-assembly for the internal representation of functions, stack allocated memory only. The motivation for these restrictions have entirely been due to my specialized continuation passing paradigm. The reality is, I came up with the CPS paradigm first. The type system only came after. With that said, when I initially achieved my CPS paradigm, I did so using a proof of concept version of it. Not only that, but truth be told, it was also meant to be a vehicle for me to learn about compiler theory. There was a lot of original research on my part having to do with CPS abstract machines. As for lexers and parsers, they are known technologies, but it was my first time building those as well. As such, the version 1.0 of my proof of concept code was a mess. I did spend time cleaning up that code in a version 2.0 proof of concept library, but even with that effort, it was still a mess. My metacompiler used a wide range of constexpr and my metacompiler used a wide range of constexpr and template metaprogramming tricks, all the while upholding a generic style of design choice. To clean up the code further, it wasn't a matter of incrementally improving the architectural design. The design had simply reached its limits. This is why I switched to rebuilding my metacompiler using a C++ constexpr functional type system. Truth be told, there's not a whole lot of design to discuss here, nor code to show at this point. The small amount we're showing starts with an example of the type system internal representation. To be clear, no one is expected to know how to read this in order to use my library. I'll explain its reading anyway to demonstrate the major design. Okay, so to start, the very first record in a type system is always metadata. The 104 is the length of the flat array. The 28 is the current length. The initial 0 is an error code. In this case, no error. The other 0 tells us whether or not the second record is a table of contents. Okay, so for the next record, next, every other record is of this form. Records grow forward from left to right. So there's a left side. The left side is the record entry. Here, the initial 5 is the entire record length. And then there's the right side. The right side is metadata. It points to the next related record. The indexing is relative, meaning it references records going backwards. Note, in my library, such record systems are called concords, and I will use that terminology interchangeably with type systems. So I create a type system this way. Surely C++ has the maturity to make type system implementations easier than this. Yes and no. constexpr is on its way with C++ 26, but not as much with 17. So why concords? First, a type system implemented as a flat array negates the constexpr allocation problem. Concord objects are always pre-allocated on the program stack, and as class definitions, they hold no internal pointer members. Second, as flat arrays, which are readily serializable, they mitigate against slow compile times. Consider the following string literal. I won't explain that, but it represents an important context-free grammar in my library, and as a string literal, it can be marked constexpr. In turn, a compile time parser generator in my library then translates it into the parser transition table for a specific metacompiler. As for compile times, my original proof of concept metacompiler didn't scale, but it was still reasonably performant. It took about 6 seconds on average to translate this context-free grammar at compile time. My current library is a bit slower. The initial step in translating the context-free grammar is to lex the string into a list of words and tokens. This currently takes about 9 seconds. Also, I'm averaging between GCC and Clang, so it works for both. If instead I write that list out to file, then read it back in during the next compilation round, rather than starting from scratch each time, it takes under 1 second. With C++ 26 and the embed feature, it might be even faster. Third, in terms of flat arrays, compile time concords are naturally compatible with meta-assembly bytecode. I've previously implemented a proof of concept virtual machine to evaluate meta-assembly bytecode directly. I'm researching how best to add it to my library. If nothing else, though, these concord objects can be used to model all variety of compile time programs in C++, with many practical coding applications down the road. And any meta-assembly within those concords, they can be used to generate functions at compile time. So one major possible application is embedded domain-specific languages, making it easy to build all variety of C++ functions. Another example is an alternative to C++ concepts. The theory of functional types includes the ability to represent mathematical claims and their proofs. A simple example of a claim being this, which reads, for all rational A and B, there's a rational number between them. So I gave a talk in 2025 on this topic, titled A Universal Data Structure for Compile Time Use. As a potential alternative to concepts, proof theory has trade-offs that might make it relevant in certain contexts where concepts aren't, but such is beyond the scope of this talk. As for other applications, to end this section, I myself intend to use the techniques of this talk along with my library to build the required compiler tools for my multimedia programming language. So as for lessons learned, the research presented in this talk is the culmination of 10 years of trial and error coding. In a longer talk, I could have discussed so much more in-depth examples. In any case, after all said and done, what lessons have I learned? One, modern C++ is a multi-paradigm language. It has great potential to express and solve many computational problems, but this also means it has a complexity of interoperable features. Two, compiler tricks are fun. And yet, it's still better to use standard language features when possible. For example, I didn't even mention the const-eval keyword and how it generally provides better type safety, feature support, as well as performance for compile time only functions. Three, compiler tricks are worth learning. Don't forget, constexpr functions and classes can and do take template parameters. The rollout of constexpr has been slow, having started with minimal features in C++ 11. Each new C++ specification is doing its best to add more standard grammar to the world of constexpr, but as of yet, there's no specification which supports all C++ features. And so there are still situations where TMP tricks are required. Even then, I've learned it helps to organize one's repertoire of tricks around narratives and theories. This is to say, standard ways of thinking. In our case, we chose the theory of functions as our technology of mind. And maybe, just maybe, the final lesson here is that technologies of mind are the ones which might, in fact, persist in an ever-changing world. So, this is the end.